Our next speaker is from the neighborhood, from Wake Forest School of Medicine. Dr. Tim Hughes is a research scientist which focuses on vascular and metabolic contribution to brain abnormalities commonly seen in aging and Alzheimer's disease-related dementia. He has several leadership roles in several large NIH-funded studies. He closely worked with a large research team of MR physicists, neuroradiologists, and a diverse group of investigators. His overreaching research goal is to identify modifiable risk factors and treatment strategies for the prevention of age-related dementia and cognition dysfunction. Today, he'll be talking about health disparities in cardiometabolic health and ADRD. Dr. Tim Hughes.
Thank you. And thank you so much for this gracious invitation to be here virtually with you today. Greetings from Winston-Salem, just down the road from you all right now. Today, as we mentioned, I'm going to talk about how cardiometabolic health may be a key factor relating social determinants of health and several models of ADRD pathology. I have no relevant disclosures to report and receive funding from several institutes within the NIH. So what I'd like to share with you today in a brief outline is how cardiometabolic disorders promote health disparities in Alzheimer's disease and related disorders. Some of you may be aware of this already. Cardiometabolic disorders may also be a key feature that will connect several frameworks that seem disparate in our Alzheimer's research realm. Those would be the health disparities research framework that I'm sure Dr. Hill will allude to in his talk later today. The ATN or framework for Alzheimer's disease and related dementias, and also the vascular contributions to cognitive impairment and dementia, or VCID. I'll touch on these frameworks and show you how they may be united by cardiometabolic disorders. Each of these frameworks is absolutely essential to study what we do in Alzheimer's and related dementias, but each of them may be insufficient to understand this problem of health equity research in AD. And I'll give you an example of a new multi-level cohort approaches that we're using to unite these frameworks. So we're all well aware of some of the health disparities that exist in Alzheimer's disease and related dementias. Dr. Doraiswamy earlier spoke about the sex differences that we see. We've touched on some of the racial and ethnic differences with increased risk for women and African Americans, Latinos. But really, these are very basic understanding of what we know so far, and they raise a lot of research questions and point to gaps that we hope to address in the near future if we are going to do something about health equity, because it will require aligning various research frameworks to do so. So one of the key frameworks that we talk about are the multiple pathways to dementia. This figure was shown in the ADRD Summit recommendations from 2019. And you'll see some of the key players here for Alzheimer's disease and related dementias, such as amyloid, tau, and neurodegeneration that form the ATN framework that was discussed yesterday by Dr. Chenji Jiang. And it's important to recognize that this summit and other summits have recognized that hypertension and diabetes are among the key modifiable risk factors for Alzheimer's disease and related dementias. And we've heard a little bit about this so far, and we'll take a dive into these topics today when we talk about cardiometabolic health. Health disparities and social determinants of health are actually key drivers of cardiometabolic health, promoting disparities in hypertension and diabetes and cardiometabolic health in general. So these, under the framework of the NIA Health Disparities Research Framework, there are very useful levels of analysis in which we can employ to understand the relationship that social determinants of health contribute to cardiovascular diseases and also ADRD. And these pillars are environmental, sociocultural, behavioral, and biologic. And in this upper right-hand corner of the biologic, you'll start to see the comorbidities in cardiovascular disease as a key player. These drive cardiovascular diseases themselves. And we're all well aware of the health disparities in hypertension and diabetes that exist among traditionally underrepresented groups in research studies of ADRD. And in particular, African Americans or Black individuals in the United States have higher rates of hypertension, have higher rates of diabetes, and also that is shared by Hispanic individuals when compared to non-Hispanic whites. But the incidence of diabetes is actually increasing over time, which could be compounding the problem that we will see when we think about the contributions of cardiometabolic factors to Alzheimer's disease and related dementias. When we take a look at how health disparities contribute to ADRD, it tells us a little bit about a connection where the two may come together into the vascular contributions to dementia. So let's build a little bit on what Dr. Zhang presented yesterday on the racial and ethnic disparities that we know about in AD and ADRD in the ATN framework. And it's these racial differences in dementia pathology that are proposed to underlie the observed disparities in AD. However, as Dr. Zhang presented yesterday, there are conflicting data on ATN biomarker studies. For amyloid PET has been found to be higher, not different or lower in Black individuals compared to white individuals. CSF, A beta 42 and 40 levels are consistently not different to a scale that we would expect to see if it was a key driver. Tau appears from preliminary results appear to not be different among Black and white individuals. And interestingly, CSF tau, total tau, and p-tau levels may actually be lower in Black individuals. There appear that there may be some racial differences in brain structure, such as lower hippocampal volumes and lower cortical thickness in Black participants compared to white participants. But in general, the ATN framework appears so far to lack the ability to differentiate the observed disparities in AD and ADRD that we see. The vascular contributions to cognitive impairment and dementia is a framework in which we are trying to understand how vascular disorders contribute specifically to changes in brain at the cellular level or at the microstructural or macrostructural level that may impact the risk for developing Alzheimer's disease and related dementias. There are several vascular factors that have been linked to brain health later in life, such as atrial fibrillation, heart failure, arterial stiffening, and these affect cerebral perfusion and the risk for stroke and the risk for dementia. When you look at the neuropathology on autopsy, what you'll find is that in general, the most common form of pathology is a commingled pathology of cerebrovascular disorders and amyloid beta among people who are suspected to have Alzheimer's disease. So one of the approaches that we can use is to start to move beyond in epidemiology studies the syndromic diagnoses of dementia and subtypes of dementia, and start to use biomarkers from MRI and from PET, CSF, and plasma to begin to look at forms of pathology that exist in the brain that may underlie the syndrome that we are seeing in our participants as they age. And these can include large artery infarction, pushing individuals more towards vascular dementia, evidence of small vessel disease that contributes to mixed dementias and Alzheimer's disease. And then, of course, the hallmarks of Alzheimer's disease, amyloid and tau. One of the things that we are particularly interested in is studying the pathways that lead to developing structural abnormalities in the brain and how vascular disorders contribute to that through the development of atherosclerosis or arteriosclerosis in the brain. Both of these are affected by vascular risk factors such as hypertension and diabetes that progress, that contribute to their progression over time. And these can be considered upstream vascular measures that, if they are truly related to dementia, we should be able to find pathways that connect them through forms of pathology in the brain, observable by imaging or biofluid biomarkers. So our approach is to leverage subclinical biomarkers to point towards vascular pathways that may be underlying the relationships between vascular risk factors, cerebral small vessel disease, and AD pathology, and cognitive decline among diverse cohorts of older adults. And again, it's important to understand that a lot of these drivers have even more upstream determinants from social and structural determinants of health. So let's start with a case study that summarizes about a decade of work from our group and others of how factors like arterial stiffness are associated with dementia-related pathology and cognitive impairment. A lot of these data come from cohort studies, and what they find is that individuals who have compliant arteries have a low pulse wave velocity, a measure of the speed at which the pulse travels. They also tend to have lower blood pressure at different regions of their body. And of course, the most important aspect is both the flow and the pulsatility at which the pulse travels to the brain. And people who have normal arterial stiffness or normal pulse wave velocity tend to have generally healthy brains and a lower risk of developing neurocognitive problems. In contrast, when the speed and pressure at which the pulse travels to the periphery can impact kidney function, liver function, and also in the context of what we're most interested in here is that it is associated with the presence and extent of cerebral small vessel disease in the brain, measured by aspects like lacunar infarcts, white matter hyperintensities, and cerebral microbleeds. And further, it has been related to AD pathologic hallmarks of Alzheimer's disease. We've shown that greater arterial stiffness is associated with the extent of amyloid deposition in the brain, and recent work with CSF biomarkers have shown that arterial stiffness is also associated with tau abnormalities with hyperphosphorylation in the CSF. In general, we can start to understand the ways at which vascular disorders can impact brain health by taking this approach of linking with these biomarkers to understand these relationships. So one way that we're extending this is building a multidimensional study in a diverse cohort of older adults. The multi-ethnic study of atherosclerosis has been ongoing since the year 2000, and over the past 20 years, it has published more than 2,000 papers looking at the determinants, prevalence, and progression of subclinical cardiovascular disease and metabolic disorders such as diabetes in the context of a regionally and racially diverse cohort of 6 sites around the United States. At baseline, 38% of participants were recruited to be non-Hispanic white, 12% Chinese, 28% self-reported as Black or African American, and 22% self-reported as Hispanic. The cohort size was 6,814 at baseline in the year 2000 to 2002 and ranged between the ages of 45 to 84. One of the reasons we were interested in looking at this cohort is to be able to take the work that we've done with subclinical vascular biomarkers and really add dimensionality to it. So I'm showing a few of the biomarkers that fall into some of the pathways that we're most interested in that may link vascular disorders and cardiometabolic disease to brain health. Those include atherosclerosis, arteriosclerosis, small vessel disease in the periphery, and cardiac function. So in 2018, we launched the multi-ethnic study of atherosclerosis MIND study, in which we're recruiting from each of the 6 sites 2,500 adults to complete detailed and repeated cognitive testing and brain MRI at 2 visits, here denoted by Mind A and Mind B. And in a subset of individuals at 3 sites, we began conducting amyloid PET imaging to measure the aggregation of amyloid deposition in the brain. We're leveraging the data of all of the prior visits of MESA to understand how vascular disease begins, progresses, and how it relates to metabolic disorders. So the way that we're doing this is by providing 3T MRI from the full cohort at 6 sites. And this processing allows us to identify regional differences in brain volume and cortical thickness, to quantify multiple aspects of cerebral small vessel disease in the brain, and also cerebral blood flow abnormalities. As I mentioned, we're doing amyloid PET with the Pittsburgh compound B at 3 sites of Wake Forest, Columbia, and Johns Hopkins. And the main cognitive endpoints that we're interested in this study is leveraging some of the existing MESA screening battery that was implemented in 2010 to 2012 to be able to track global cognitive decline now over more than 10 years. And adding to this, the uniform data set that was mentioned at the end of the questions in the last talk that's used by all Alzheimer's centers to define domain-specific cognitive performance and allows adjudication of cognition, which is ongoing right now for our first visit that just wrapped up. So I'll show you a little bit of data on how vascular factors such as vascular risk scores and glucose variability over time are relating to cognitive decline and brain structure in this diverse cohort. So one of the reasons to look at vascular risk scores, to start there, is that these are clinically meaningful and easy to measure risk scores that allow us to understand the risk for developing both cardiovascular events and also the vascular contributions to dementia later in life. Here we'll be talking about the Framingham stroke risk score, and in this sort of mosaic diagram here, what we're showing is the overlapping components in the center of these 3, and also how they differ on the far edges. The atherosclerotic cardiovascular disease pooled cohort equation is intended to be a measure that is more for atherosclerotic disease and allows us to differentiate general vascular risk from atherosclerotic risk. And then also the cardiovascular risk factors, aging, and incidence of dementia, or CADE risk score, that was developed and is used as a screening method within the pointer studies and worldwide finger studies, which adds to the mix of these vascular measures more dementia-focused measures such as BMI, physical activity, education, and ApoE genotype. Each of these risk factors varies across the racial and ethnic groups in MESA. And in general, the CADE risk score, which was developed in primarily European white individuals, is elevated in both African American and Hispanic participants in MESA. The Framingham risk score is only significantly higher in Black participants, whereas the risk for atherosclerotic cardiovascular disease is elevated in both African American and Hispanic participants. We took a look at how this related to change in global cognitive performance between exam 5 and exam 6. So this is using a predictor to look at change that begins 10 years later, and it follows individuals over 6 years. When we look at the relationship between the risk scores and the first measure of cognitive performance, we see that higher risk scores across each of these categories are associated with lower cognitive performance across each of the racial and ethnic groups. The magnitude at which the vascular risk scores relate to cognitive decline varies across the groups, being highest in Hispanic, African American, and Chinese individuals compared to white. Looking at the relationship between these vascular risk scores and the odds of a 1 standard deviation decline is how we're showing it here. We see that every standard deviation increase in CADE is associated with a higher odds of cognitive decline in this cohort. And here we're providing the area under the curve for each of these and how much the model is predicting this odds of decline. We've recently, this paper has just been accepted and is in press now at the Journal of the American Heart Association. We've taken a first look at the brain imaging across the 6 sites. And this paper is looking at comparisons in brain volume and structure across the racial and ethnic groups. And then on the next slide, we'll look at some of the determinants of brain volume and white matter disease. So this initial set was 1,036 participants, similar to the proportions at which MESA was recruited initially, slightly higher among white participants than the baseline recruitment. And at this point, individuals are a mean age of 72 years, and about half of them were women, in line with the initial recruitment strategy in MESA. What you'll notice in panel A is that compared to the largest group in MESA, which are white individuals, there were non-significant differences in total brain volume across age among Hispanic and Chinese American participants. Among Black participants, they tended to actually have larger brain volume compared to white participants. African American or Black participants also had higher white matter hyperintensity burden, a measure of small vessel disease in the brain as well. When we take a look at some of the determinants of brain volume and small vessel disease in the brain, what you notice across the top panel is that, as you would expect, brain volumes go down per 5-year increments in age, and is also lower, significantly lower among individuals who have diabetes. When we look at, yeah.
Minutes.
Okay, great, thank you. Among small vessel disease markers, what we find is that smoking status, hypertension, and diabetes are key drivers. We took a look at a subset of individuals who also have amyloid imaging at the Wake Forest site. And what I will show you is on this next slide is that the risk scores that we looked at related to cognitive decline before, elevations in these risk scores are associated with higher amyloid deposition in the brain, increases in white matter hyperintensity volume, and lower cortical thickness. So given the 2 minutes, I will skip through the metabolic piece and summarize. So cardiometabolic factors representing subclinical vascular disorders, vascular risk, and which I didn't show the glucose results today, are associated with cognitive decline in ADRD. And in what we're doing next in this group is we're actually beginning to increase the dimensionality of what we're doing. So on the left, you'll see the framework that we're using. This framework brings together ecological models, social determinants of health, and at the bottom, health and well-being factors that include aspects of Alzheimer's disease and related dementias. And these are being extended with additional studies that are measuring neighborhood characteristics for a second time in MESA, stress over ecologic momentary assessments and heart rate variability, a second assessment of sleep in MESA, measures of 24-hour physical activity, and continuous glucose monitoring. And this will allow us to start to untangle aspects of the fundamental, intermediate, proximate, and risk factors for health and well-being. So in conclusion, I'd like to thank you for the time to speak with you today about some of the work that we're doing relating cardiometabolic risk factors to Alzheimer's disease and related dementias. By extending the work that we're doing both towards biomarkers of ADRD and also back towards the social determinants of health to understand what the drivers of these disparities may be. And we hope that this work will point to new pathways to the treatment, new targets for treatment strategies that will work across our diverse population. So with that, I'll stop and take questions if we have time.
I guess we have 1 minute and we will see if we have any questions. So there's a question, are MESA mine data publicly available?
MESA mine data are not currently publicly available because we have just finished up the first visits. They will be posted, as all MESA data are, on both 7 Bridges and also through TopMed. We are working as well to make these data available through NAC for all Alzheimer's centers as well.